We're supposed to determine whether this series converges or diverges, and they specifically suggest we use a p-series to make that happen. So this chapter in our text gives us a tool to help us make that determination. It's called the limit comparison test. The limit comparison test is where we can compare our series, at least the sequence that helps us determine our series. So we could call this our A sub n. We can compare that to some B sub n that we know of. We know that it converges or diverges. And if we divide the two series and we evaluate a limit as n goes to infinity, as the terms go to infinity, that can help us determine whether it converges or diverges. Doesn't tell us what the converging value is, but at least helps us get an idea. So if we want to compare this to a p-series we know, you could try one that diverges or try one that converges. So let's start with the one that diverges. Let's let b sub n be 1 over n. Right? This is a p-series that diverges. It's a special one. This is when like the power equals 1, so it's on the border. This is the harmonic series, and it's been shown in our text that this diverges as n goes to infinity. So this is our A sub n, this is our B sub n. Let's do what the limit comparison test says to do. We're going to take A sub n, and we're going to divide it by B sub n, and we're going to evaluate the limit as n goes to infinity. And it'll either evaluate to be some constant, some value, it'll either go to 0, it'll either go to infinity, and then we can look at our result a little bit closer and make a determination from there. So still evaluating this limit as n goes to infinity. We'd flip and multiply the second fraction, and I think you can see that it's going to make the n's cross out, right? Change that to multiply, those are going to cross out, so we have the natural log of 1 plus 8 over n. Okay, so the limit as n goes to infinity. Think about what happens in here as n gets really, really big. This fraction gets really, really small, so it's like 1 plus something approaching 0. So natural log of 1 is going to be 0. So we can just write that this limit is equal to 0. Okay, so that would be the second case. If the limit as n goes to infinity of a sub n divided by b sub n equals 0, which it is in our case, and if the sum of the terms of b sub n converge, then a sub n converges. So we made a guess using something that diverges, right? So that doesn't hold for this, for 2. These two facts don't add up. We got 0, but b sub n does not converge, okay? So that means we need to go back to the drawing board and try something. Instead of something that diverges, let's try something that converges. Let's let b sub n, let's compare it to 1 over n squared. This is a convergent p-series, so we know this converges. So repeating that step, the limit comparison test, we evaluate the limit as n goes to infinity of the natural log of 1 plus 8 over n divided by 1 over n squared. And then we would flip and cross cancel, so that's the limit as n goes to infinity of n times natural log 1 plus 8 over n. This limit's a little bit harder to determine because as n goes to infinity, you can't consider what happens is that this gets infinitely close to 0, but this goes to infinity. So L'Hopital's rule is what we're going to have to do to eventually evaluate this. Remember, L'Hopital's rule happens when you could rewrite as, the limit would be an infinity divided by an infinity, okay? And if that happens, you can use L'Hopital's rule, which means you take a derivative of the numerator and the denominator, and then you can reevaluate the limit. So it's a way of breaking down a limit that's hard to evaluate, that has problems with infinity. So I'm going to rewrite this a little bit. This is the limit as n goes to infinity. I want something in my denominator. So I'm going to do this. Algebraically, that kind of is frustrating to see, right? This is n to the first. I'm going to kick it into the denominator so that we have n to the negative first in the bottom. That way I can use L'Hopital's rule. And now if I evaluate this, I like to use this notation where I just put an L on top that says, hey, I used L'Hopital's rule. I'm taking a derivative of the numerator. So the derivative of natural log of 1 over, what did I write down here? This is 8 over n. I got those flipped. When you take a derivative of the numerator, that's 1 over 1 plus 8 over n. And now we need to multiply that by the derivative of the innermost function. So the derivative of this is negative 8. Sorry, the derivative of the innermost function is negative 8n to the negative second. And then the derivative of the denominator using L'Hopital's rule, that's negative n to the negative second. So let's see if that helps us evaluate. We have an n to the negative second in the numerator, n to the negative second in the denominator. So let's cancel those out. And then while we're at it, we'll cancel out the negative signs. So after using L'Hopital's rule, we actually have something a little bit simpler. This is 1 over 1 plus 8 over n. And then there's a times 8 that I dropped down there. So this limit we can evaluate. The limit as n goes to infinity. This term gets close to 0. So 8 over 1 is just 8. So that would be this condition here. The limit came out to be L. In this case, L was 8. Then, so since that condition holds, then A sub n and B sub n both converge or both diverge. This is a convergent p-series. And since we have 1 checked off, and since B sub n is convergent, then this is convergent by the limit comparison test.